So this is experiment 4, the last distillation of Organic Chemistry 1 lab. This is fractional distillation, and we're going to use gas chromatography to analyze the separation of 2-methylpentane and cyclohexane. Simple distillation is great for solvents that are similar in the sense that they are miscible, but they've got a wide range of boiling points. We say generally 40 degrees. 2-methylpentane and cyclohexane are miscible with each other. However, the difference in boiling point is 18 degrees. So they're very closely boiling. Therefore, we cannot just use simple distillation. We use something called a fractional distillation in a fractionating column. So rather than using the spin vane in this particular instance, we're still using the 5 milliliter reaction vial, but instead of the spin vane, we instead have this fractionating column. It's still made out of Teflon. There's a magnet in there so that it'll spin, but you'll note that it's threaded here. So this is a threaded column, and essentially what it's going to do is each thread, so to speak, if I can focus, each thread here is going to act as like an individual still. So remember that in simple distillation we saw the vapors climb up the Hickman-Hinkle still head and heated the glass. In this instance, it's going to heat the Teflon. And so there's going to be an exchange here, 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 and here, rather than just one exchange with the attached glassware. So this fractionating column has something that's equal to more than just one, what we call theoretical plate. And so you're urged to read the lab manual about theoretical plates and gain some more information and knowledge about fractional distillation. In terms of setup, is identical. And we are going to add the same amount of each liquid. It's going to be 1 milliliter of, this is cyclohexane. We don't want to make that mistake again. We made this mistake one year. Cyclohexane smells awful. We need cyclohexane, and then, good thing I looked at that, 2-methylpentane. All right, so we're adding 1 milliliter of cyclohexane and 1 milliliter of 2-methylpentane. These are both pure, sold by Alpha Azar and Spectrum. So remember, we're using 2 automatic pipettes. We've got it set to 1,000 microliters, which is equal to 1 milliliter. And so the first liquid I'm going to draw up is cyclohexane, 1 milliliter. And then the lower boiling 2-methylpentane. And now we've got our hot sand bath with the heat setting around 5 to 6 already set up for us. So we're going to attach the 5 milliliter reaction vial with its fractionating column in there to the Hickman-Hinkle still head attached to the Claisen adapter. Straight up and down is our digital thermometer so that we could get the range of boiling point. And of course we want to be able to stir this thing, otherwise we won't have fractional distillation. So the rate of stirring needs to be very carefully controlled, because we don't want to have this create a vortex where distillation is either slowed or sped up. So if it's going too slow, that's not great, but if it's going really fast, then it's just going to push everything upward, and we no longer have an actual fractional distillation. Use this alcohol thermometer to push the sand around. So this is about a decent rate. And so we're going to watch this carefully and try and be sure that the Teflon doesn't expand too rapidly, because occasionally it can get stuck in the neck right there at the 1410 joint. But right away you can already see that the 2-methyl pentane is starting to boil. And so once again, rather than just condensing on the glass, it's the liquids are going to be condensing on the column as well. And there's going to be a heat exchange between the vapor and the liquid of the higher boiling cyclohexane. So each of those little threads can act as a little heat transfer, sort of like a molecular dance between cyclohexane and 2-methyl pentane. So when this occurs, you get enrichment of the lower boiling solvent, and that's what we are expecting to come off firstly. So this is still the same. Our first fraction should be enriched with the lower boiling compound, the 2-methyl pentane. Since the refractive indices of both solvents are so similar, rather than using a refractometer to calculate the percent composition of each fraction, we will be using gas chromatography. So this is a very sensitive instrument that will be able to give us very accurate readings of the actual percentage of 2-methyl pentane versus cyclohexane in both of our fractions. So while I've been speaking, you can see that the reflux, the vaporization and condensation of the 2-methyl pentane is going on here. So again, that's all that occurred. It was on the glass with the simple distillation. This is now also occurring with the fractionating column. Up here we've got the thermometer probe, and then the well of the Hickman-Hinkle stillhead, where we're going to collect our 2 fractions. I'll say, so now our 2-methyl pentane boiling, the distillate has reached the probe of the thermometer. So we're starting now at 63.8 degrees, and then once it starts making its way over that well, that's when we're going to start recording our temperature. And so it's there now. We can see the volume. So this is 64.7, and so this is going to be the starting range of our first fraction. So 64.7. You always want to keep a good notebook. So we see that that first fraction, the volume is going up in the still head, and we've got a nice stir rate. So hopefully we're going to get very decent separation. The temperature is 67.1 degrees. When we see it dip a little bit, then we'll hope that then all of the 2-methyl pentane has distilled over, and the cyclohexane boiling at 80.7 will be the next thing to come up. But this is rising pretty rapidly, which makes sense because it's lower boiling than the other 2 compounds than we were using the last time. Even though the laboratory is freezing, we don't have to use a aluminum tent this time. So it's 68.1 degrees. 68.2. And rather than a sample vials, we are going to be using these little snap vials, which will be used by the GC instrument. And so I've got 2 little vials here ready for fraction 1 and fraction 2. And we're going to collect it like we have before through here, and always use a new pipette each time. So we're at 69.2. So this still, we're hoping, is enriched in the 2-methylpentane. I'm going to label my fractions, fraction 1 and fraction 2, just so I don't get mixed up later. So 69.5, it's really holding right there at 69.5. And now it's decreasing a little bit. So this is, we're going to say, our first fraction. We are not taking a second fraction here. And I would say that definitely looks like a milliliter to me. And so I'm going to cover this. The snap for this is pretty easy. And now this should be ready to go for our GC instrument. I'm going to discard this glass pasture pipette in the glass waste. And now we're waiting for the cyclohexane to come over. So this was 69.5 degrees Celsius was our boiling point range for fraction number 1. And now we're seeing 70.7 to blank. And what we might do is take a little bit out and call that a second fraction, so that it's rinsing the well, because it's still not close to the boiling point of cyclohexane. So this is an adjustment to the procedure. This second fraction is now going to be 2 of 3. So similar as we did for simple distillation, we're going to take 3 fractions this time. So the third should be mostly enriched with cyclohexane. And we'll admit that the second fraction is going to be a mixture of the 2. And GC will tell us exactly how much. Holding steady at 73.3. So this might truly be the end of all of the 2-methylpentane. I'm going to hold the probe directly center so that it's not touching the walls of the glass. I want it just to give the reading of the vapors. So we're at 75. Let's cut it at 75.5. This is fraction number 2. You really don't need much for GC analysis. You need about, sometimes you can even go as little as 0.1 microliters. So now we can turn the heat up because we know that the remainder is cyclohexane. So we're starting here at 76.4 now. And remember that the boiling point of pure cyclohexane is 80.7, but it's somewhat suppressed because there must still be some 2-methylpentane. This isn't a perfect fractional distillation. If we had a longer column, then it would be. It would be a better separation. The more theoretical plates that you have, the better the separation. I'm going to hold this again. So now this is 80.6, 80.7. So that's our cyclohexane for sure. And looks like we're all dry in the pot, the distillation vessel, our 5 milliliter reaction vial, so we're good. So we've gone to 80.7, which is the boiling point of cyclohexane. So I also want to see if I can get a good picture of this. So when I open this cap, you can actually see a plume of the vapor. So let's see if the video can record that. Not really. But anyway, got to switch pipettes. So back again with the brand new pipette. And now fraction 3. Is all set to go. So that was fractional distillation. Pretty straightforward. The more difficult part to explain, in addition to the actual theoretical plate idea and fractional distillation, the theory behind it, is also then going to be the theory behind gas chromatography and how the instrument is actually going to be able to help us determine the percent composition of 2-methylpentane versus cyclohexane in these 3 fractions here. And so we've got someone that's an expert in instrumentation that will hopefully help us out in the next video, but for now we can at least show you the instrument. So this is our Agilent GC, and so that sample vial is going to go in one of these wells, and essentially what happens is that this robotic arm is going to come over, pick it up, spin it around, and then a needle is going to drop down and auto-inject it into the column, which is in here, which is contained in an oven, and we've got this copper coil, and the sample vaporizes, and it's going to separate the 2-methylpentane from cyclohexane very efficiently, and then it'll read out data at the computer where it'll measure the area under the curve for each of those that's detected, and give a very accurate measurement of the amount of 2-methylpentane versus cyclohexane in each of those fractions. So there will be a more thorough discussion in the next video.